Now, we might think, if I asked you all, this is, again, another insight into how difficult the word forever is. If I asked you how many rationals are on the number line, you would probably say there's an infinite number of rationals. On top of that, you'd probably say there's an infinite number of counting numbers. And you probably say there's an infinite number of irrationals on there. And all of that would be pretty kind of correct. But we're going to find out that they're actually different in the quantity, so much so that if you randomly put your pencil on a number line, you are 100% guaranteed that your pencil will fall on an irrational number. That the likelihood of you choosing a rational or counting number from the number line at random is not almost zero, but literally 0% likely. We're going to kind of dig into that here. All right, so follow me if you will. If you have any questions, feel free to let me know. We're going to take two different facts here, and we're going to combine them in a creative way. Here's the first fact. I can represent the fraction 1/9 as 0.1 repeating. And you can use a calculator if you'd like to verify that. If you don't trust the calculator, you can do it with long division. It's totally going to work. Also, I don't have to represent it as a decimal. I could represent it as a series of fractions added together, because we call this the tenths place. This is 1/10. So I can represent that as 1/10. And this is the thousandths place. So I can represent it as 1,000th. I can put that over here as the hundredths place. I can put that as the hundredths. And then I've got the thousandths place. So this is the equivalent way of being able to describe 1/9. Either of these work. They create the same thing. So that's fact one. Fact two is that if I am creative, I can create a matrix, a list of every fraction number that is in existence. Okay, so here's how I've organized it. I've started off, we got 1/1. If you go down the matrix, you can see that that's now 2/1 and then 3/1. So we're going to change the numerator by 1 every time we go down a row. And we're going to change the denominator by 1 every time we go over a row. Now, we're only doing the positives here just for simplicity, but we could absolutely do the same thing with the negatives, and we're not going to change the result at all. So right now, I just want us to recognize that this has every single positive number that could work as a fraction, as a number of the rationals. Let me make sure where I'm drawing from. There we go. So what we're going to do is we're going to zigzag through this matrix, and we're going to make a list. So we're going to take this, we're going to zigzag through it. And from that zigzag, I can make a list where I start with 1/1, and then I go to 1/2, and then I go to 2/1, and then I go to the next row would be 3/1, and then from there I go to 2/2. So if I repeat a fraction, that's fine, but I'm just simply saying I can list them all, and I will get to them all. So those are the two facts. One, I can make a list that has every single fraction number in it, and two, I can represent 1/9 as a bunch of addition. All right, those are the two facts. Let's take a look at how we can creatively use those. Imagine now that instead of just having 1/9, I'm going to make this 1/9 of an inch of ribbon. So 1/9 of an inch of ribbon. Here's some ribbon. And I cut it off of my little spool. I've got 1/9 of an inch of ribbon, and I'm going to take that 1/9 of an inch of ribbon and I'm going to cut it up more. And I'm going to use the little pieces of that 1/9 to cover places on the number line. So I'm going to cover the number 1 with the first cut, this 1/10. I'm going to cover it with a 1/10. And then I'm going to go on to the next number in my list, and I'm going to cover it with a 100th. So I'm covering up every single number on the number line with ribbon. Now, once I've covered up the number 1, we'll agree that there's some excess. So I've definitely covered up 1, and I've even covered up some numbers off to the side. That's fine. I'm just simply saying we can cover up every single rational number with some ribbon, and that it's not going to be a total amount of ribbon more than 1/9 of an inch. All right, so 1/9 of an inch of ribbon is all I need to cover every fraction on the number line if I'm creative about it. Thus, the rationals must be together no bigger than 1/9 of an inch. You want to talk about the negatives? Fine. Repeat the exercise over there. You get 2/9 of an inch. Like we're just covering, like I can cover it all up with ribbon. And I can cover it all up with a specific amount, 1/9 of an inch of ribbon. Well, there's nothing special about the 1/9 of an inch of ribbon. We could repeat this again with a 90th of an inch of ribbon. I could start with a 90th of an inch of ribbon, and then recognize that that fraction is that I don't have the tenths anymore. I just start with the hundredths. and then that's plus the thousandths. So in other words, I can go through this whole thing again and I can cover up the number line. I can cover up every fraction with less ribbon, but I still cover everything up. Well, I can repeat this again, and I can cover it up with less ribbon. I can cover it up with a 900th of an inch of ribbon. So now I must be able to cover up all the fractions with less than that even. Well, I can repeat this game again and again and again. So that means the total size of the rationals must be some size that I can cover up with a 1/9 of an inch, a 90th of an inch, a 900th of an inch, and however small I want to go. Well, then that means it must be a size that can always be covered up by smaller. There's only one size that works for that, and that would be 0. So that means all of the fractions, the size of all the fraction numbers, if you took all the rationals, you pulled them out and you grouped them together and you measured it, they have no size. There's zero in measure, 0 in total amount of the number line. Now that's weird, because the consequence of that is if you have the number line and we split it into the rationals and we split it into the irrationals, then that means that all of the rationals take up no space. That means that the irrationals take up all the space. That means most of the number line, not most of the number line, all of the number line size is due to irrational numbers. There are so many more irrational numbers than rational numbers. So all the rationals add up to just 0 in length. The irrationals, on the other hand, add up to all of the length. And this again shows us a weird paradox that infinity is present in. That means that if we think of all of the rationals, all the fraction numbers as just being 0 width numbers, 0 width points, they're just points and points and points, and we add them together, that's a bunch of 0 plus 0 plus 0 plus 0 equals 0 for the rationals. But for the irrationals, even though every number still has no width, we do 0 plus 0 plus 0 plus 0 a whole bunch of times and we get infinity. So we had a whole bunch of zeros added up to a 0 and then a whole bunch of zeros added up to infinity. Like that's about as opposite as you could possibly get. What's happening here? Well, the consequence that I want you to take away from all this is think about this. Everything you thought is a normal counting rational size in your life, most of them aren't. Your height, like I'm 6'2", I'm not 6'2". I'm an irrational number that's pretty darn close to 6'2". There's like, I am not a rational height. Your desk is not a rational area. Volumes, none of the volumes you've ever encountered in your life ever have been solid, normal, nice. No, they're all irrational because they exist on a continuum of measurement. And if you choose a number from that randomly, you are guaranteed for it not to be rational. So anybody who's like, oh my golly, like the calculator didn't give me a nice answer. Yeah, expect that out in the real world. That's how the real world works. If you want to have like nice numbers, you better be talking about something that's not on a continuum. Like sure, one pencil and another pencil makes 2 pencils. Got it. You're not going to have 2.1 pencils. But if it can exist on a continuum, if there's the ability for in between, the entire world actually exists as an irrational measure.